Welcome to the second part of our OLED tutorial. Today we're going to show you how to simulate device properties using LightForge, however not using material parameters set manually, but instead using material properties computed automatically with the microscopic sub-workflow from first principles. Once again, I'm going to share this webinar with my colleague Franz Maller. I will give you an introduction in the microscopic sub-workflow, so show you how to generate morphologies with parameterizer and deposit, and then run subsequent electronic structure analysis using QuantumPatch. Franz will then show you how to load the output of this electronic structure analysis into LightForge and guide you step by step through the setup of a OLED device simulation based on Ab-Initio input. The model system we are simulating today is a bilayer OLED, or at least the emission system. It consists of two layers of the molecule DPA illustrated to the left and the molecule DPPQ in the right layer. As Franz will explain later, we will include additional layers, however, for simplicity on a parametric level. So let's get started with the morphology generation. As explained in the first part of the tutorial already, we generate atomistic morphologies of our layers, of our organic layers, by mimicking physical vapor deposition in our simulation tool Deposit. In our simulation tool Deposit, we start with an empty box and then therefore deposit one molecule at a time. So we add one molecule to the simulation box, and it then is being relaxed thermodynamically to find a thermodynamically optimal configuration or equilibrated configuration on the substrate made up by already deposited molecules. As you will see highlighted here in purple, we do this with a couple of simulation steps and also heat up and cool down this molecule in order to being able to hop between local minima and then find the thermodynamically really equilibrated state. Once this molecule is deposited, we just keep adding molecules until the sample is high enough. The input that we need to generate morphologies are XYZ coordinates of the single molecules, if possible pre-optimized, but we have the parameterization model to optimize the atomistic coordinates with DFT, and the output of deposit are thin film structures with atomistic resolution, and they can be either pristine layers, but we can also obviously deposit mixed films or deposit interfaces. The morphologies we get out of deposit feature commonly observed PVD anisotropies, and you can also observe the built-in potentials that sometimes are generated when depositing thin films. For normal-sized molecules, the deposition of one of these films, say about 1,000 molecules, takes only a couple of hours. You can see the full workflow required to generate morphologies illustrated on the left side. So we have three modules. You have the parameterizer module, which optimizes the molecular conformations as explained before, but also computes customized force fields for the intermolecular interaction. So classical functions that are quite efficient to evaluate, where we can compute the interaction between the molecules during the deposition process. The second module is the dihedral parameterizer module. Here we basically pass on the optimized conformations from the parameterizer module and then compute the intramolecular interaction. So basically we allow for single dihedral rotations and compute the energy profile around these rotations and plug it or basically wrap it into a, again, molecule-specific force field. These force field parameters are then automatically passed on to deposit, which I have explained in the last step, the protocol mimicking physical vapor deposition, and out we get, as illustrated below, the thin film morphologies. In the following, I'm going to show you how to deposit a bilayer morphology of this emission system we are looking at with SimStack. What we need to do is to run basically all the modules for both molecules. So we start with the parameterizer and dihedral parameterizer module for the molecule DPA, then continue with the parameterizer module and dihedral parameterizer for DPPQ, and plug each input in one of the deposition modules. We start with the deposition of DPA and then deposit DPPQ on top, resulting in this interface morphology. Okay, so we switch to our workflow platform SimStack that you know already, and we can simply start to construct the workflow by dragging and dropping the modules that we need. So we start off with the parameterizer module for the first molecule and the dihedral parameterization for the first module. You can switch the order here of these modules also via drag and drop, and again add a parameterizer module for the second molecule, and once again the dihedral parameterization that you need for flexible molecules. Then you add the deposition which will generate a layer of 1500 molecules of the first molecule of DPA, and then we use this as input for the last module, for the last deposition, where we deposit 1500 molecules of DPPQ on top of the DPA film. All the input that we need are Mo2 files of single molecule structures of both DPA and DPPQ, and we have them here in some directory. You can visualize them using, for example, JMol. So look at the DPA molecule. Here we go. And also the DPPQ molecule. And this can, for example, come from some chemical drawing tool which can do some sort of pre-optimization to generate a 3D structure. All right, so what we do is we're going back to SimStack and double-click on each module to load the input and define the parameters. We start with the parameterizer module, and you see here the field Mo2 file, so you can click on the list icon next to it to load a file from the hard drive, and the button right next to it is basically to load input from other modules, which we do not need in the initial modules, but in the subsequent modules. All right, so we go on the list icon, go to the directory. In this case, it's in webinars, Ab-Initio device, and load the DPA Mo2. And we can do the same thing for the second parameterizer module. Double click on it, and we see here again that we need to specify the input. So we again go to webinars, Ab-Initio device, and load the DPPQ molecule. This is basically all we need, and all other input is, or the input of other modules is passed on from previous modules. The settings of the parameterizer modules we can set now. We leave charge and multiplicity, but what we want to do is optimize the molecule, so we also leave this option checked. We want to compute partial charges and optimize the molecule with turbomole, so the engine is already set. However, the engine settings we need to adapt. We want to use B3lib as a functional and def2svp as a basis set. Here we go. And run a pre-optimization with DFTB. If you do this, then the geometry optimization with turbomole takes far less computational time. This is all for this module. The only thing that we need to specify now is the computational resources that we want to use. So we go to the Resources tab, click the checkbox, and in this case choose 32 cores, and we want to have 64 GB of memory. All right, so we do the same for the second module. We keep the optimized molecule checkbox checked. Oh, sorry, this was the second module, so sometimes it's confusing. So we need to go to the first module, to the first parameterizer module, keep the optimized molecule button checked, but change to B3lib and def2svp here. And again, go to the Resources tab, allocate 32 cores and 64 GB of memory. All right, to compute internal or force fields for internal degrees of freedom, we use the dihedral parameterizer modules. So we double click on the first dihedral parameterizer module, and here now we use the second option to load input. Namely, we do not load input from the hard drive, but rather use the output of the parameterizer 3 module, which is listed in this drop-down menu, namely the molecule PDB, and in the second field the molecule.spf, which contains the initial set of force field parameters. As evaluation engine, we once more switch to turbomole, as usual B3lib and def2 svp, and keep the rest as is. We again need to allocate resources, so we use 32 cores and 64 GB of memory. And we do the same thing for the second module, second dihedral parameterizer module. However, keep in mind that you now need to load the input from parameterizer 3-1 and not parameterizer 3. So we load from the drop-down menu the molecule PDB from parameterizer 3.1 and also the SPF file from the same module. Again, switch to turbo mode, choose B3lib and def to SVP. Alright, allocate resources, otherwise it will take forever. 32 cores, 64 GB of RAM, and there we go. What you can do every now and then is to save the workflow either by pressing Ctrl S or by going to File, Save As, and we give it a name. We call it morphology, call it bilayer morphology DPA DPPQ. Press the OK button and you see that now the workflow appears in the bottom left workflow panel. When you close and reopen SimStack, you still find this workflow, and you can open it again by just double clicking on it, and you find it with the same exact settings as you placed there before. Now we go on to the deposit modules. This is where we actually generate the thin films. Again, double clicking on these modules shows the respective settings. The parameters here are basically half the box size in angstrom. It's a bit confusing. However, so if there is a value of Lx of 40, this means that the simulation box goes from -40 to +40 angstrom in x direction, and also here in y direction. Z is the deposition axis, so we need to make this a bit larger. Usually we go for 120 angstrom if it's a single layer. Now we want to do a large interface, so we make it a bit larger in this case. If you have larger molecules than the molecules we use right now, we would recommend to increase this value to say 50 to avoid edge effects. However, in this case 40 is just fine. Later we want to extend the morphology in XY directions to create enough environment for QuantumPatch for the electronic structure analysis. So we enable the periodic boundary conditions here, which means that molecules being deposited on one side of the thin film also feel the molecules of the opposite side as neighbors. So we want to deposit 1500 molecules, and we have two temperatures that we need to set. One is the initial temperature of the annealing cycles and one is the final temperature. So during the deposition we heat up and cool down the molecule a couple of times in order to enable an efficient sampling also across energy barriers. We leave the acceptance temperature as it is, increase the number of simulation steps to 130,000, which has proven to be a good value, and choose a total of 32 simulation annealing cycles. As the molecule is quite flexible or has these two single bond dihedral angles, we enable the dihedral moves. Okay, so now we need to specify the input, so we go to the molecules tab, and again we load the output of the respective dihedral parameterizer modules as input for deposit. So for the first deposition we choose dihedral parameterizer 2 molecule PDB and dihedral parameterizer 2 dihedral force field.spf, and since it's not a mixed film but a pristine layer, the mixing ratio is 1. So for example, if you would want to do a mixed film, we could use the plus button to add a next molecule, a different molecule to this film. We go to the resources tab, and as in the last modules, specify 32 cores and 64 GB of memory. In the next deposit module, you see that we still need to set all these parameters, and it's in this case important, since we want to deposit on an existing morphology, to use the same box parameters for both depositions. So in this case we used 40, 40, 150 and enabled PBC, and we want to do the same here, 40, 40, 50, enable PBC. Also we want to do 1500 molecules. We set the temperatures also to, or the final temperature also to room temperature, increase the numbers of steps to 130,000, use 32 simulated annealing cycles, and enable the dihedral moves. So we see by double clicking that the settings are basically the same for both modules. Again, we go to the Molecules tab, and now we choose the output from dihedral parameterizer 1 as input. Same for the force field file. And here we go. Now we still need to tell the second deposition that it wants to use, or that it should use, the output of the first deposition as a substrate. So we check this restart from existing morphology button and load from the deposit 3 module the restart file as input. Now we go to the resources tab once more, specify 32 cores and 64 GB of memory. And we're basically done with setting up the morphology, the workflow to generate the morphologies. Again, we store the workflow either by pressing Ctrl S or by going to File and Save. Then it will save it in the already named workflow. What we now would do if we want to do only the morphology generation, we press the Connect button to connect to our computational resource, then go to Run and press Run. However, as I will show in a couple of minutes, we also want to include electronic structure analysis in the same workflow. So we just save it for the time being and continue later with the same workflow. To motivate the electronic structure analysis, I would like to use the example of charge transport. As you know, charge transport in organic semiconductors can be described via hopping transport due to strong localization of the atomic orbitals, of the electronic orbitals on the molecules. And one theory which can be used to describe the charge transport is Marcus theory. You see here the Marcus rate of a charge transport between an initial molecule with the index I to a final molecule with the index F. And without wanting to go into detail, there are 3 basic ingredients to this. The first ingredient, highlighted in green, is the overlap of molecular orbitals, or sometimes referenced to as electronic couplings, which we can compute using DFT wave functions. The second ingredient is the reorganization energy. So if you charge a molecule, you have a change in geometry, which is connected to a change in energy, and this also enters this rate equation. And the final ingredient in blue, and basically the most important one, is the energy difference of a charge sitting on the initial versus the final molecule. In order to properly describe charge transport in organic semiconductors, we need distributions of these quantities, especially for the electronic couplings and the energies. So what QuantumPatch does is read in the morphology from deposit and then run pairwise computations of these molecular orbital overlaps and compute distributions of orbital energies. As molecular properties change between a molecule in vacuum versus a molecule which is embedded in a thin film, QuantumPatch generates or computes these quantities, taking into account basically the unique environment of each molecule on a full quantum mechanical level. In order for you to be able to understand the settings that we later set in QuantumPatch, let me give you a brief introduction to the QuantumPatch approach in general. As I mentioned before, it's crucial to take into account the electrostatic environment of each molecule for which you want to compute a quantity. So we always define a core shell, highlighted in red, which contains the molecules for which we want to compute, or on which we want to compute the quantum chemical properties. We have then different shells for the environment with a different, say, level of accuracy. So in this case, we would have 2 dynamic shells, one in dark purple, one in a bit lighter purple, and one static outer shell in green. For molecules in the dynamic shells, we also take into account polarization effects. So molecules in the dynamic shell are equilibrated, also taking into account the surrounding molecules, while the molecules in the static shell are basically computed in vacuum to generate an environment for the dynamic shell. The equilibration of the full sample is then basically, as illustrated in the bottom left, an iterative execution of single molecule DFT or DFTB computations in the core shell and in the dynamic shell to equilibrate the electronic structure of each molecule individually by taking into account surrounding molecules in form of partial charges. To compute excitonic properties, we have the Exciton preprocessor modules, in short EPP. So we need to compute the ingredients for several excitonic processes, such as, for example, TTA, illustrated in the top left, so triplet annihilation, or TPQ, illustrated in the bottom right. So we compute molecular properties such as excitation spectra for single triplet cation and anion, but also phosphorescence and fluorescence, transition dipoles for all the molecules, in order to compute excitonic rates for all processes such as TTA, STA, TSA, TTF processes, but also singlet-singlet annihilation, and the interaction between excitons and polarons. What we will then do just in a minute is to extend the workflow as we constructed it before by 2 QuantumPatch modules and 2 Exciton preprocessor modules. With the first QuantumPatch module, we compute homo-LUMO distributions, so energy disorder. With the second QuantumPatch module, we compute electronic couplings. And with the Exciton preprocessor modules, we compute excitonic properties for both molecules. Just as a remark, usually we should also compute IP and EA as transport levels. However, for simplicity, we use HOMO and LUMO in this study. For more accurate studies, please refer to IP and EA and check the respective tutorial and how to compute them. Back in our workflow panel, we can now simply add the QuantumPatch modules and Exciton preprocessor module to this workflow to compute the input we just discussed that we need for later charge transport and exciton dynamic simulations. So what we do is we add 2 QuantumPatch modules. I'll explain to you in a second why this is. So basically we have QuantumPatch 3 and QuantumPatch 3.1, and we also add 2 Exciton preprocessor modules, for which I also tell you in a second why we need 2. All right, starting with the Exciton preprocessor modules, which is the more easier setup, we double click on the preprocessor module and we can then here input the morphology. You can either load the morphology from the POSIT or a single molecule file from the parameterizer, for example. In this case, we recommend to use the single molecule from the parameterizer module, as it is quite expensive to compute distributions of all these quantities, and usually the quantity of a single molecule is sufficient. We then enable fluorescence, phosphorescence, TTA computation, and the exciton polaron interaction input here, and go to the engines. In the engines tab, we need to adapt especially the turbomole1 engine, so we set the function again to B3lib and the basis to def2 SPP. And in this case, since it's only a single molecule computation, we can increase the numbers of threads to 31 and the memory to 6000. The number of threads here is basically limited by the numbers of cores that you can allocate. We need 1 master thread out of for technical reasons. So if we allocate 32 cores, we need to limit ourselves to 31 threads here. If we go back to the Generals tab, we see that in addition to the turbomole engine, we also apply the Dalton engine for the fluorescence part. So we can also go to the Dalton engine defined here and use multi-threading here. However, we only use 16 threads, as this is quite this is still working reliably for Dalton. All right, so now for the shells, we set list of molecule IDs and simply type A0, which means that it will take the first molecule of the single molecule file that we provided. We need to set the same settings for the second Exciton preprocessor module, but instead of the parameterizer 3 molecule PDB, we choose the output of the second parameterizer module, so we run the computation on the second molecule. Again, enable all these options and go to the Engines tab to adapt the engine settings. Again, we choose B3lib, def2 SVP, set the threads to 31, 6 GB of memory, go to the Dalton engine and also use 16 threads and 4 GB of RAM. Then go to the Resources tab, allocate 32 cores, 64 GB of RAM, and what we forgot to do just now is in the Shells tab, go to a list of molecule IDs and specify the first molecule with the ID 0. For QuantumPatch, again, double click on these modules to see the respective settings. Here for both QuantumPatch modules we will load the interface morphology, which is the output of the second deposit module. So we choose deposit 3.1 structure PBC CML. The structure PBC CML is basically the deposited morphology but extended in XY direction periodically to generate sufficient electrostatic environment for the core shell. We have two QuantumPatch modules here because in the first module we want to compute energy disorder, so energy level distributions, and in the second module we want to compute electronic couplings. In principle, this could be done in the same run, however it's computationally more efficient to split it into two parts. In the first module we therefore disable the calculate chase button, and also we don't want to do in vacuum lambda EIRP calculation, and please disregard the molecular state at this stage. We then go to the engines tab, and what we need to have is one engine for the core shell, one engine for the first self-consistent shell, one engine for the second self-consistent shell, and one engine for the static outer shell. For the core, we just label this then TM core, sorry, caps lock, TM core, and for this shell we choose turbomole, however with B3lib and def2SBP, and keep the rest as is. For the first dynamic outer shell we also use turbomole, but we call it TMN for turbomole environment, switch here to turbomole and use indeed BP and def2SBP and keep the rest normal. For the second dynamic outer shell and the static outer shell we run DFTB, and we can just keep the settings as they are. Now we go to the shells tab, and here in the shells tab we basically define the shells as I explained before. So for the core shell we go for number of molecules of each type, and we want to run this on 200 molecules of each type. So we choose the innermost 200 molecules of DPA and 200 innermost molecules of DPPQ. The engine here is already set to turbomole core, so we can go on. As explained before, we need 3 outer shells. We use the plus button to add one more outer shell, and then go on by using the TMNF engine for the first dynamic shell with 15 angstrom. We use the DFTB engine for the second dynamic shell with 25 angstrom radius, and we use DFTB plus for the outer static shell, which has 60 angstrom radius. In this case, we can disregard the lambda EIRP tab and post-processing tab and directly go to the resources tab here. QuantumPatch scales quite well, so the more cores you have, the merrier. In this case, on our resources, I would go for 64. So one node on 64. I could even do, say, multiple nodes with 64 and allocate 128 gigabyte of RAM. So take whatever you have. We can once again remember to save the workflow so all your work isn't wasted in case of anything crashes. The second QuantumPatch module is in order to calculate chase, so we only disable the in vacuum part and again disregard the molecular states. Once more, we load the output of the second deposit module, so deposit 3.1 structure PBC CML as input. The shell setup is quite similar, however we only need one turbomole engine here because we can use the same engine in the core shell and in the first environmental shell, which runs with the BP86 functional. So indeed we can just use turbomole 1 as one engine and DFTB as a second engine and switch to the shells tab. Again, we choose numbers of molecules of each type. However, in this case 80 per type should be sufficient. We use the turbomole 1 engine in the core shell and the turbomole 1 engine in the first outer dynamic shell, and add one more engine for the second dynamic shell, however with DFTB with a radius of 25 angstrom, and also a DFTB static shell with 60 angstrom radius. Again, we go to the resources tab to allocate as many resources as we have. In this case, I will go for 2 nodes and 64 cores with 128 gigabyte RAM per node. Before coming to an end, we save this workflow. We save it as microscopic DPA DPPQ. And with this, so you see once more that it appears in the bottom left for reload later. And with this, I would like to hand on to my colleague Franz Maller, who will guide you through how to set up LightForge simulation using the output of this sub-workflow as an input.
I will continue this tutorial showing you how to set up the final device simulation. We start going to the bottom of the workflow and dragging in the LightForge Vano. We double click the Vano and add electrons and excitons, because of course we want to simulate a full OLED. We have electrodes attached to inject the current, and automatic periodic boundary conditions, which means there's periodicity perpendicular to the transport direction. Now we go to the I/O tab to manage inputs and outputs. We use inputs from QuantumPatch, so we keep this field checked. The first input will be the input for the energy levels, so we give it the name energy. The energy levels were calculated in the run QuantumPatch 3, so we select here QuantumPatch 3 analysis zip, which contains all the simulation results required for this LightForge run. We add another output file for the couplings. We call them short J's. They were calculated in QuantumPatch 3_1, so we add analysis zip of this QuantumPatch calculation. We add another QP output file for the Exciton preprocessor calculation of DPA. We give the input the name EPP for Exciton preprocessor, DPA for diphenylanthracene. And we chose the simulation Exciton preprocessor analysis zip. Now we add another output file for the Exciton preprocessor calculation for DPPQ. So we give it the name EPP Exciton preprocessor DPPQ diphenylpyridoquinoline, and we add the output file from the Exciton preprocessor _1 analysis zip. With this we have finished importing the necessary input files, and we go on to define our materials. The first material will be DPA. It shows input mode QP, AIP sigma and par lambda, which means the AIP values and disorder values will be obtained from input files from QuantumPatch, and the reorganization energy value, which short lambda, we will enter manually. Input mode excitonics, we choose Ab-Initio plus preset. That means all excitonic properties which were calculated in the Exciton preprocessor will be loaded from the corresponding file, while properties which were not calculated are loaded from the chosen Exciton preset. We have to choose a molecule PDB so that LightForge can identify the correct input data from the QuantumPatch calculations. So we choose parameterizer 3 outputs molecule PDB, which was the run for DPA. QP output sigma. Here we have to select our input file from which the energy disorder is gonna be extracted. This is the file energy. The IP is also gonna be extracted from the same input as is the electron affinity. As we did not calculate IPs and EAs explicitly, this will use the HOMO and LUMO levels which were calculated in QuantumPatch. Please note that there's a significant difference between HOMO, LUMO levels and electron affinities and ionization potentials. So for a more accurate device simulation, in particular with materials which are less similar than these, please do an explicit IP and EA calculation and supply the corresponding input here. The QP output excitonics for DPA, we choose here the input EPP DPA, which we defined earlier. For the reorganization energy, we put both for hole transport and for electron transport 0.2 electron volts. As the Exciton preset, we keep the default preset fluorescent. As we import Exciton data from the Exciton preprocessor, most parameters of the Exciton preset will be overridden. If I click Show Exciton preset and locate the fluorescent preset, I can see the different preset parameters. The radiative singlet and triplet decay rates are imported from the Exciton preprocessor. The thermal decay rates are however not calculated in the Exciton preprocessor, and the values from the preset are used. All quenching rates from TTA to SPQ are calculated based on the input from the Exciton preprocessor, so these values here are ignored. Intersystem crossing and reverse intersystem crossing rates, however, are not calculated by the Exciton preprocessor, and the values from this preset are used. The relative light absorption is imported from the Exciton preprocessor. The reorganization energy is not imported, so this value is used. The binding energy is calculated from the values from the Exciton preprocessor and from the EA and IP values. The energy disorder is imported from the Exciton preprocessor. The singlet triplet gap is imported from the Exciton preprocessor too. Now we define our next material. The PPQ. As with DPA, we extract energy levels, mean values EAIP and the disorder sigma from QuantumPatch and input the reorganization energy lambda parametric. We use the Ab-Initio input for the Exciton preprocessor. So here the three energy values we keep. Exciton preprocessor, we use the input file EPP DPPQ. And the reorganization energy, as before, we put to 0.0 electron volts for both electrons and holes. This OLED is designed so that excitons will be generated at the interface between DPPQ and DPA, and light generation and quenching should also happen then near that interface. To confine excitons to these layers, though, And to prevent leakage currents, we will add also an electron and a hole blocking layer adjacent to these two materials. Since for our analysis we are more interested in the active part of the OLED, meaning the light generating part, we will use semi-parametric layers for our hole and electron blocking layers. On the DPA side, we will add another layer which will use both DPA morphology, DPA couplings, DPA energy disorder, but we will change the average EA level to act as a strong electron blocking layer. And on the DPPQ side of the device, we will add a hole blocking layer for which we just use the QuantumPatch input which we calculated for DPPQ, but we define the IP level manually so that it acts as a hole blocking layer. Of course, we could have also searched for a separate EBL and HBL material with the appropriate properties, but for convenience we chose to use the DPA and HBL molecules and just modify the relevant electronic properties. For the EBL and HBL materials, we define the average EA and IP levels parametrically in such a way that on the EBL side we match the HOMO of the EBL with the DPA, and on the DPPQ side such that we match the HBL EA with the DPPQ EA, in this case the DPPQ LUMO. In order to do it exactly like this, we require the knowledge about the DPPQ E LUMO and the DPA HOMO, which are a result of the QuantumPatch calculation within the workflow. This means if you have no prior knowledge of your materials and you have never run a QuantumPatch calculation of these materials, you cannot take this shortcut if you want to match the energy levels exactly, because the average HOMO and average LUMO are of course only a result of this workflow. Of course, alternatively you can separate the workflow in two workflows. You first run the workflow until LightForge and then you set up the LightForge run separately. So we add now another material for the EBL. Call it EBL. And as input mode we choose sigma from coupe and parametric EAIP, so the average energy levels and the reorganization energy. Exciton inputs we'll just take from the presets. The molecule PDB would be the same as the molecule PDB of DPA, so that's parameterizer 3 molecule PDB, which is the one we also chose here. Energy inputs are taken from the output energy. The IP level we saw on the table before. It is 4.7 to match exactly the IP level of DPA. To have a very strong electron blocking layer, we leave the EA at 0.0 and we put two reorganization energies of 0.2 electron volts respectively. Now DPA has a very high singlet triplet gap, so to avoid any exciton transitions at the interface from the DPA to the EBL, we will also need to use a preset here which has a very high singlet triplet gap. In case of DPA we don't need that preset because the exciton information is loaded from the Ab-Initio calculation, but for this parametric material we have to define it. So we define an additional Exciton preset by clicking Show Exciton Presets and clicking plus. Go to the bottom, and we will define an Exciton preset for a high singular triplet gap, identical to the one we used in other parametric tutorials for TTF OLEDs. We call it high ST gap. We increase the singlet decay rate. We decrease the triplet decay rate as there's no phosphorescence in this material. We increase the singlet triplet gap to 1.25 eV, decrease the exciton binding energy to 0.3 eV, and that's it. Now we go to our EBL material and we choose as an Exciton preset the newly defined high ST gap preset. Now we add another material for the HBL. Again, we will only read in the disorder from our QuantumPatch input, so we choose here sigma for disorder from QuantumPatch, the rest parametric. We will again use only an Exciton preset for the excitonics of this whole blocking layer. As before, we choose the preset with a high singlet triplet gap. We choose the molecule PDB input file, which will be the one for DPPQ, as the HBL layer here borders DPPQ. We will just use the same material with its modified energy levels, and we put in the modified energy levels here. To block the holes, we put an IP of 7.0, an EA of 2.33 to match the EA of the DPPQ, and reorganization energies of 0.2 electron volts. Now, having defined the required materials, we go to the Device tab to set up our device. We choose a width of 18 nanometers. This is the size of the periodic simulation box perpendicular to the transport direction. The first layer, which will be the electron blocking layer, we choose to be very thin, just 6 nanometers. And the material is here the EBL. We add a second layer. Thickness of 10 nanometers. This will be DPA. We add another layer, also with the thickness of 10 nanometers. This will be DPPQ. And last, fourth layer, the thickness of 6 nanometers again, which will be the whole blocking layer. Now we have to modify our electrodes for charge injection. For the hole injection, we put a work function of 4.3 electron volts, and the coupling model will be parametrized. We slightly increase the inverse electron wave function decay length. You could also leave it at the default parameter. This will just slightly increase simulation efficiency. It will not change the results of the simulation. For the second electrode, through which electrons are injected, we choose a work function of 2.9 electron volts, and also parametric transfer integrals for the charge injection. Now Since in this simulation we do not simulate explicit doped injection layers, we use the electrodes as effective injection layers. So we choose the energy levels close to the energy levels of the doped in injection layers that we would usually have. As a morphology expansion scheme, we choose EDCM. This determines the algorithm which constructs the morphologies of the different layers based on the radial distribution functions or nearest neighbor distance distributions from the morphologies which we created using deposit. Next, we go to the topology tab. We start by defining our max neighbors. We put a very high value here of 120. This is the number of neighboring molecules to which charge transfer rates will be calculated. So 120 is a large number, but this number will be cut down automatically if we also check the box to prune transfer integrals. We leave here the default value, which will erase those connections from these 120 which have non-appreciable transfer integrals. As transfer integral source, we choose QP output as we calculated transfer integrals using QuantumPatch. First step transfer rates will be automatically calculated based on the input from the Exciton preprocessor. Now, for every pair of molecules, rather molecule types, we have to define the input. For DPA, we use as input for the transfer integrals the file Js. For DPA, DPQ, we also use the file Js. For DPA EBL, we also use the file Js. For DPPQ, oh, excuse me, I just did a mistake here. That should be here. I changed the already defined pair. For DPPQ, we also use this input. Now for DPPQ HBL, of course, we also get our input from the file Js. And last, for HBL likewise. Oh, not quite last, we forgot EBL rather. So now we have all combinations from neighboring molecules. Next, we go to the physics tab. As a rate model, we choose automatic. We keep the checkbox for super exchange checked, which will enable long-range hops through virtual states on intermediate bridge molecules, and by that enhance hopping distance. We also activate a Coulomb correction for the Exciton binding energy. Now we continue with the operations tab, where we define the simulation parameters such as temperatures and applied fields. First, we enter here a number of simulations of 15. This means for every field value we will do simulations in 15 different disorder configurations to enhance our statistics. We have a calculation with direct current, temperature of 300 Kelvin, and now we have to input the fields which we want to calculate. Since we use two very different work functions, as we use them as kind of effective injection layers, we have to look again what kind of work functions we used here. It was 4.3 and 2.9. So I'll just enter this here to remember it. And we have a device thickness of 6 plus 10 plus 6 plus 10 nanometers. So we divide the voltage drop due to the work function difference by the thickness of the device. We also add 2 times 0.8 nanometers, which is the default distance to the electrodes. And by doing this, we get the inbuilt voltage, which we have to compensate with an applied electric field. So here we have an inbuilt voltage of 0.042 volt per nanometer. So to have an appreciable current, we start our simulation with 0.055 volt per nanometer, so roughly adding 12 milli electron volts per nanometer to the field, which just compensates for the inbuilt voltage. Now to sample a range of voltages, we just add 10 millielectron volts per nanometer to that. And another time, and then we put in a field which is a little bit higher to see the efficiency roll off a bit better. We don't need any initial particles since we have electrodes attached. Now we have to fill out this box with the convergence criteria. Now we don't want an automatic convergence criterion via the fluctuation of the current, so we put this very high, and we will just determine the end of the simulation by entering the number of simulation steps we want to simulate, and we put here 600,000. The max time here of 100,000 seconds, it will not be reached with any normal device. Now we go to the Analysis tab, check this box, and we activate Exciton lifecycle analysis, which gives us a detailed picture of the different states an exciton go through in the device operation. Auto run start we put at 0.1. This means quantities which are used for the analysis are recorded after 10% of the device simulation. Now we save our workflow. Okay, and we define the resources for the simulation. To do this, we go back to the Operations tab. We see we have 4 fields, we have 15 simulations, so that's 60 independent simulations. So we would like to allocate at least 60 worker processors plus one managing processor, which is 61 processes. So we put here 61 CPUs per node, one node, and 64 gigabyte of RAM. You could also, if you don't have a node with these many cores, you could also put here 2 nodes and 31 cores each. Now you would be ready to submit the entire workflow. You might have noticed that we cheated a little bit with these electron and hole blocking layers, because we already knew the HOMO and the LUMO level of the DPA and the DPPQ materials, and we matched the HOMO of the EBL to the DPA and the LUMO of the HBL to the DPPQ. Of course, you could not do this if you were completely in the dark about your material properties. So in that case, you would first do the entire workflow until LightForge, and then do a separate LightForge run. Of course, if you do not want to do any things like these, like adding non-full Ab-Initio layers with matched energy levels, you can also just run the entire workflow without any prior knowledge. Although then also care has to be taken that the attached work functions are appropriate. After we have ran the entire workflow, we can inspect the results of the device simulation by going to the Jobs and Workflow tab and selecting our workflow. For this video, we ran the LightForge workflow separately from the preparatory Ab-Initio workflow. So now we only see here the final LightForge icon. If you run everything together, you will also see the icons for the different Vano modules. I can download a zip archive with all the analysis results from the device simulation if I download results.zip. But I can only, I can also interactively look at the results by doing a right click on here the LightForge icon and pressing Browse Directory. We start by locating the results folder. Then we go to the material folder, energy levels, and here we see for the 4 different fields a band diagram of the device. On the left we see the electron blocking layer, on the right the hole blocking layer, and in the middle the interface between the EBL, between DPA and DPPQ. Here this being DPA and this DPPQ. If we look at a higher field, we will see that the slope of the bands changes. Now right clicking and going on back, we go further back and we go to the experiment section of the analysis. We go to current characteristics, and first we are going to look for a file called trajectall.png. This shows the conversions of the simulation. What we see here in 4 different colors are the 50 different simulations per field. So in blue that would be the strongest field, in black the weakest field. On the x-axis we have a measure for the cumulative charge displacement in units of the device length. So we can see that for all fields the charge has passed an appreciable distance with a more or less constant slope, so this is a well converged simulation with regards to the current density. We go back and we locate the file iv.png. This shows the current voltage characteristic of this material in ampere per square meter. So in milliampere per square centimeter, this would be a factor 10 smaller. Nevertheless, we see we have a quite high currents, as we have basically no barriers in our device and low disorder materials. Now we go back and we locate IQE PNG, and we can see the internal quantum efficiency with respect to the current, and we can see that this has a very low internal quantum efficiency, starting by 4% and with a roll-off going down to below 1%. To analyze what deteriorates the efficiency of this device, we go back a second time and we go on particle densities, and we locate first, to get an overview over the situation in this device, the files at the bottom, quenching density average. We have 4 files here for the 4 different fields, so we will look at it for, say, field number 1, and we see in this bottom panel in red the average hole concentration per our 80 nanometer cross section, and in blue the average electron concentration. We see that our electron concentration at the interface is smaller than the hole concentration, which means in general an electron comes to the interface where a hole is already waiting for the electron. However, we still have an appreciable electron concentration, so this means the 2 charges need some time to find each other before they can recombine, which is not optimal, of course. We see in black in the top panel that most of the quenching occurs basically at the interface, right where the excitons are created. To analyze this further, we go back. We remember that we were looking at field number 1, so we locate the file exciton decay density average 1 total.png. Here we get a spatially resolved overview of different excitonic processes. In blue we see most of the recombination happened at the interface. In yellow we see also there's a appreciable amount of charge separation, so this means the excitons form at the interface, they wander around and they also separate again, which is an effect which is also enhanced due to the energy disorder, but of course it is an unwanted effect. On the right here we have this legend, and we see in red SPQ, so singlet polaron quenching. We have in green singlet triplet annihilation, which seem to be here quite dominant loss processes. We also have PTQ, which is a Dexter based polaron quenching mechanism. It is noteworthy that the gray bars seem to be here and here, so far away from the interface. So when an exciton kind of managed to diffuse away from the interface where we have a high charge and exciton density, there seems to be a higher chance for radiative decay. We go back to look at some further analysis. We see that we have other files here which are called exciton decay density average 1. So for this field but it says species 2, 3, 1 and 0. This means we have this spatially resolved Exciton decay plots also resolved for the specific species. So 1 being dPA, 1 dPPQ, 2 the EBL I think, and 3 the HBL in the order we defined them in the materials tab. So we can, for example, here click on the EBL and we see there are no exciton quenching events on the EBA. So the EBL was not involved basically in any of the excitonics happening in this device. But if we click on the file for dPPQ, we basically see the right part of the plot, which gives an overview over all species which we saw before. Now for some further analysis, we look at Exciton life cycle 1 HTML, and this gives us an overview over the different stages of the Exciton life cycle. So you read it off starting in the middle. This is where excitons are created. They are created either as triplets, here in brown, or as singlets, here in purple-ish. These are excitons which already existed before we started recording excitons for the analysis, so we don't know how they were created. However, it's only a small fraction of excitons. So what happens to triplets next? We can see if we hover our mouse here over this orange bar, and we see in the box that occurs, it's called separate HE, which means that the exciton separated again in an electron hole pair by way of an hole hopping to a neighboring molecule where the exciton stays on the where the electron stays on the molecule on which the exciton was. The reverse separation event is here on the opposite. It's separate electron hole. This means the electron hops away, whereas the hole stays on the location of the exciton. Below you can see this live mole type. This tells us where this separation occurred. Now it occurred only on type 0, 46 times. Type 0 here is a dPA. So if we look on the separate HE, we see that it only occurs on type 1. So this is interesting because this basically tells us that the charge separation here is basically the reverse of the recombination. If we are on type 1, which is dPPQ, a hole is basically just transferred back to dPA and the exciton is separated, and here if you're on type 0, an electron is transferred back to dPPQ and we lose our exciton. However, since we don't lose the electron hole pair, this is not necessarily a loss in efficiency. It's just for the simulation that you might have basically a cascade of recombination and charge separation. Other events that happen for the triplets here are end tracking. Basically that means these triplets still lived at the end of the simulation, so we don't know what would have happened afterwards. So in blue we see move charge. This is a Dexter-based polaron quenching. So our exciton was destroyed basically by interaction with a polaron. Here in this pinkish color we have Dexter EPT. That means the Dexter-based also exciton polaron transition. So it's also quenching due to Dexter-based polaron quenching. And here, very small, we see a triplet fusion. So two triplets fuse to become a singlet. What happens to them here, to these poor little singlets? Half of them is quenched due to STA, singlet triplet annihilation, the other half due to SPQ, singlet polaron quenching. So a similar picture if we just look at the singlets. Here we see basically an even number is created on the DPPQ and the DPA, and we see now next they are either quenched, most of them by STA, singlet triplet annihilation, or SPQ, singlet polaron quenching. So I think we can already speculate this OLED might have a higher efficiency if we would confine the excitons on one side of the interface and only to a few emitters, which also might not be accessible for charge, so might be charge traps. This might already give us some direction how to improve this rather simple device. Now in orange we see again charge separation, and here very small in light blue there's some radiative decay. But mostly what we can take away from this is that we have almost everything is destroyed by singlet triplet annihilation and singlet polaron quenching. And also that we have only a very small amount of triplet fusion. Now we go back again and we click on Exciton Lifecycle 3 HTML, so the strongest field. And what we see is a similar picture here with for the singlets STA and SPQ, but we also see that we have a little bit more triplet fusion than we have before. So we have a little bit a few more singlets due to triplet fusion, but still only a negligible amount compared to direct combination to singlet. Documentation of additional analysis you can find on our website docs.nanomatch.de. Go to OLED software manuals, LightForge output, and you will see a short description of the most important outputs for OLED simulations.
Alright, this concludes our webinar today on Ab-Initio simulation of OLED devices. As you may have noticed, for some material properties we did not compute the parameters from first principles. We did this for simplicity because this webinar was meant as an introduction. So what we have not looked at was the Ab-Initio computation of ingredients for doped injection layers, here illustrated in green. The Ab-Initio computation of absolute energy transport levels. So as noted before, we used HOMO and LUMO instead of EA and IP, and also reorganization energy we supplied manually instead of computing it from first principles. All this, however, is possible. You can find tutorials on the respective links listed on this slide. You can also find a complete instruction of full Ab-Initio OLED simulations, so really full Ab-Initio OLED simulations, for example, for the setup illustrated in the top right, available in the link below. However, please note that this is quite advanced, so we suggest that you start with simulating one of the simpler stacks and then continue with increasing complexity. So thank you very much for watching. Please let us know any comments or questions you have, so write us an email at info@nanomatch.com. Also, please check out our webpage, especially the virtual lab webpage, where we provide documentation on various use cases, including step-by-step guides on how to set up and analyze these simulations. So once again, thank you for watching and goodbye.